In yesterday's class, we started looking at feedback systems, more specifically negative feedback systems. So, the basic idea in negative feedback is that you have a desired quantity, okay, or you have a desired level of some quantity, and you want to drive another quantity towards that desired value, okay. And this, as I pointed out, negative feedback is a very common or a very a fairly universal concept in engineering, right? If you take a mechanical system, maybe you wanted to run at a certain speed, move at a certain speed, you wanted to rotate at a certain speed maybe, okay. In electrical engineering, maybe you want the motor to run at a certain speed, maybe you want the voltage to be a certain value, okay. Or maybe it could be in aerospace where you might have something, it might be something to do with the missile, right? There are a whole bunch of applications, okay? But this is a very general concept. What you're trying to do is figure out, okay, what you, first of all, figure out what your desired value is and drive a certain parameter towards that design value, okay, towards that desired value. And you have what is called a controller which actually drives that particular quantity. In this case, SO is the quantity, okay, that you want to have a certain value, okay. SI is the input, okay, and you might want SO to be driven towards SI or maybe a certain fraction of SI, a certain multiple of SI, and so on. And this involves several steps. The first step is to measure the output quantities, okay. If it's a physical parameter, let's say temperature, speed, etc., you will have a sensor or a transducer which will convert that physical quantity, a mechanical quantity, etc., into an electrical quantity, okay. If it's already an electrical quantity, you're already good to go, okay. It's already in the form of a voltage or a current or something else. Then next step is to compare the actual value with the desired value. So the actual value is the instantaneous value of S0, okay. The desired value may be Si, okay. And then finally you input something to the controller such that the output, such that the actual value is driven towards the desired value. Is that clear? Any questions on this? This is just a very generic feedback concept. I expect actually this should be fairly intuitive, right? I would think. Okay, so this involves measurement. Okay, that's number one. How do you do comparison? You subtract the two. That's the simplest way of comparing two quantities. You have the actual value and the desired value. You take the difference between the two. That gives you a measure of how different they are. Your final objective should be to set this difference to be equal to 0. So you generate an error, in this case SE, okay, and use that error to drive the controller such that SO is driven towards the desired value, okay. And this is simply a summer with a positive and negative sign, with a plus and minus. Now, very specifically in the case of electrical engineering, okay, we are interested in using negative feedback to build an amplifier of gain K, okay. Now before we go there, the controller itself, we need to understand what the controller is composed of, and we saw that a controller itself should have some form of integration going on inside, okay, and there is some other parameter, so it basically takes this error, integrates it and drives the output, and there is some constant of proportionality omega u which we will not worry about in this course. You will study about it in future courses, okay, but the point of the matter is omega u right now we'll assume it is there only for making sure that the dimensions are okay. Now let us say that we want to actually build an amplifier of gain K. So we basically have an input voltage Vi, okay. The desired value is K times Vi. We want to drive the output to K times Vi. So this is what we want to achieve at the end of the day. Okay. Now, of course, the simplest way to achieve it you can use a voltage controlled voltage source. Since we know there are elements called controlled sources, we can actually use a voltage controlled voltage source. But as you might have seen from the tutorials, the typical elements that we have called transistors, the two types of transistors that we looked at, had looked more like voltage controlled current sources. Okay, so if you want to generate, if you want to create an amplifier using a voltage controlled current source, you will need to build something like this. Okay, you apply the input, you generate a current which is proportional to that input voltage, you run that current through a resistor to generate a voltage. Okay, now what this, the output voltage will be taken across the resistor RL, and very clearly GM RL should be equal to K. So far so good? Any questions on what we have seen so far? Very good. Now how do we do this? We said you have some quantity, okay, you have the controller, we need to look at what it is composed of. But basically the point to note is that GM itself may be a function of this value. GM itself may vary with several different parameters. Very clearly it is going to be a function of the operating point if you build it using nonlinear devices. So therefore we need to figure out a way to get an amplifier of gain exactly equal to K without relying on GM to be exact. Is that clear? So we are starting to build an amplifier. So we have VO, okay, we have VI. Now I first need to measure VO, okay. Now I can measure VO, compare it with K times VI, and then drive VO towards K times VI, but I cannot generate K times VI. That is exactly what I want to generate. So what I am going to say is, compare VO and K times VI is the same as compare VO by K and VI. Right? If VO by K is driven to be equal to VI, I have achieved what I want to do. I hope you all see this. I want to get VO to be K times VI. In other words, I want VI to be VO by K. Right? So if I am able to measure, if I am able to generate VO by K and compare it with what I already have, which is VI, okay, then I can go ahead and drive the controller appropriately. So first I need to generate VO by K. Okay, the easiest way to generate VO by K is to use what is called a resistive divider. Okay, I run it through a pair of resistors of value R and K minus 1 times R. Okay, the voltage here is going to be VO by K. Is that clear? That's my first step. So I generate VO by K. Now I need to compare it with VI. How do I compare it with VI? I know how to do that also. I generate the difference between the two, and I use that to drive the controller. That I'll call the error voltage. VE is VI minus VO by K. Okay, and this is an integrator which is going to integrate this error and generate VO. Okay, what is going to happen? We know that VO will not change only when VE is equal to 0. If VE was anything other than 0, okay, the controller will integrate that VE and change the output appropriately. The only way VO will reach some sort of steady state will be when VE is equal to 0. Is that clear? So this is clear. Okay. And how do we know it is going to work properly? So let us say VE was a positive quantity. Okay. So we can even start off with some certain values. Let us say VO was 1 volt. Okay. And let us say VI was 1 volt. The initial value of VO was 3 volts. Okay. This is when I'm starting to look at the system. And let us say K is 4. Okay. What is the voltage here? 3 by 4 volts. Correct? The voltage here is 3 by 4 volts. Yes.
Isn't the controller is composed of the control source?
No, it is not. It is an integrator. The control source we are going to look at, it is an integrator. Okay. A control, we are eventually going to put in some kind of control source inside, but as I pointed out, just using a simple control source will not work for us. Okay. Because this value here is not fixed, number one. Okay. Number two, this does not have any integration. Both those issues are there. Any other questions?
Can you repeat what it is?
Yes, for sure. This is the generic feedback system for electrical quantities. Correct? Now, some of these things may be composed of control sources. For example, the integrator itself, the driver, the controller, may be composed of elements, nonlinear elements that can be considered to be voltage controlled current sources. Okay. But the point is, we cannot rely simply on those control sources alone to generate this value of K. The reason is, if you have, for example, a voltage controlled current source, the value of K will necessarily depend on Gm. If you just try to use this in a very straightforward manner. Okay. So that is what I meant. Somehow you might be using these voltage controlled current sources, etc. inside transistors, inside that integrator. We will not worry about that. We are trying to look at it from a very high level perspective. This was just to give you an idea, reason why you can't directly use these. Because the first obvious thing which must come to your mind when somebody says build an amplifier, okay, of gain K using an element that you already know. Okay, if somebody says voltage amplifier, you will just say build a voltage controlled voltage source. Right, that is obvious, of value K. But that is not so easy. Yes.
Why are you making this an integrator?
Okay. As we saw yesterday, the way we analyzed it yesterday was to break the loop somewhere here and see what will happen intuitively. Okay. If you actually break the loop, okay, we considered this, were you here in yesterday's class? You were, right? We saw what will happen if the speedometer was stuck. That is what is meant by the loop is broken. Even though the output is changing, the measuring instrument is broken. Okay. What will happen? You are traveling at you have some input speed, okay, and your feedback speed is stuck to some specific value. Depending on what this difference is, you are going to accelerate it faster or slower. Okay. And I think that is what I drew here. Depending on what the value of error is, if it was this, you will accelerate gently.
Yeah, but I think you assume that it's linear. Why should it be linear? That's not
You are absolutely right. What I was pointing out is that an integrator is the simplest way to achieve this. You understand what I am saying, right? An integrator is the simplest way to achieve this. You are absolutely right. You can have different functions which will achieve the same thing. Any other questions? Okay. So let us say the initial value of Vi was 1 volt. Initial value of VO was 3 volts. Okay. VO by K was 4. We are trying to achieve an amplifier of gain 4. VO by K is 3 by 4 volts. What is VE? Is 1 by 4. Okay, the value of VE is 1 by 4. The minute this is VE is positive, what will the integrator try to do? It will increase the output appropriately towards 4 volts. If you start off from, for example, 5 volts, okay, this voltage VO by K will be 5 by 4, the error voltage VE will be negative, and the controller will drive it down. Okay, as you can very clearly see, if as long as VO is different from the desired value of 4 volts, the controller will drive it towards 4 volts, whether it's higher or lower. This is essentially negative feedback in action. Okay, so in steady state, VO has to be equal to 4. Is that clear? In steady state for this feedback system, VO will be equal to 4 volts, and as it so turns out, this particular function of comparing the two voltages, generating the difference and then integrating it, is performed by a very specific element, or to think of it in a different way, this function is so important, okay, that we have decided to create an element specifically to perform this function. Okay, this is called an operational amplifier, and it is so widely used. Okay, number one, it has its own name. Okay, number two, you can, just like you can go out and buy a resistor, capacitor, transistor, etc., you can also go outside and buy an op amp. Okay, you can, just like you can get a resistor of value 1 kilo ohm, 2 kilo ohm, 1 ohm, 2 ohm, you can buy operational amplifiers with different parameters. Okay, it is such an important element. What we will do, okay, in this course, we will not worry about this parameter omega u, because very clearly this parameter omega u will decide what the transient characteristics are going to be. We will not worry about this. You will study it in later courses. Okay, we will make an idealized assumption, okay, about this. We will come to it in a little while. So this element is called an operational amplifier. Okay, and for ease of pronunciation and so on, it is often referred to as an op amp, and it has some two inputs, V1 and V2, and one output VO. Okay, again in this course we will not worry about this omega u. We will just assume that omega u is very large. Okay, and we will say VO is some A0 times V1 minus V2. If you actually make omega u very large, okay, just take it for now that the op amp characteristics can be represented by something like this, where A0 is very large. Is that clear? Now, yesterday after class somebody asked me what these voltages V1, V2 and VO are referred to. From now on, for the rest of the course and even in future courses, if somebody just shows a voltage on a wire as V1, you can just assume that there is some implicit reference, and the voltages of any wire are always represented with respect to that reference. Okay, so there is some ground inside here, okay, with respect to which V1 is referred to, V2 is referred to, and VO is referred to. Okay, and of course often the op amp ground is not explicitly shown. It is shown only as a 3-terminal element. Okay. In reality, it has many other terminals. Apart from ground, it may very well have a positive supply, DC supply, DC voltage. It may very well have a negative supply. Okay. So it may have many other things apart from ground. It may have a positive supply, negative supply, and so on. We will just use it as a 3-terminal device because we are looking at a very idealized picture. Okay. For an ideal op amp, of course, A0 is infinity. Any questions? Okay, so now let us redraw this amplifier. Note that the signs of the op amp, I will point it out explicitly. The signs positive and negative point out how the error voltage is generated. Okay, VE is V1 minus V2 or V plus minus V minus. Okay, and V0 is A0 times V plus minus V minus. So the op amp takes the difference between the voltage inputs to the positive terminal and the negative terminal and takes this difference and multiplies it by a very large quantity. So now let us complete this circuit picture. This is VO. Sorry, K minus 1 times R. This is R. This is VI. This is VO by K. Have you seen this picture before? You might have seen this in several other places. Where have you seen this kind of picture before for this circuit? Workshop probably, right? Or maybe if you have an electronics hobby, you might have seen this. This is what is called a non-inverting amplifier. This is called a non-inverting amplifier configuration. Of course, the op amp itself can be configured to, since it's a very versatile element. In this configuration, it is being used to generate a gain of amplifier with gain K. Okay, there are many other different configurations where it can be used in many different ways. Okay, it can be used to create integrators, differentiators. It can be used to create negative gains, positive gains, and so on. Okay, so it can be used in many different configurations. In this particular configuration is called a non-inverting amplifier. Any idea why?
Because its output is the same sign as the input.
The output is the same sign as the input. Kind of. In reality, okay, so far we have been assuming that VI, VO, etc. are DC signals. Okay, in reality they can also be sinusoids or combinations thereof. Okay, so if your VI was a sinusoid, okay, this was VI versus time, okay, and VO, let us say, look like this. This is a non-inverting configuration. If you had an inverting amplifier configuration, okay, you would get an amplifier like this. You would get a phase shift of 180 degrees. Okay, this particular structure gives you only a non-inverting gain, and it gives you a non-inverting amplifier gain K, which has to be greater than 1, because we do not have negative resistors, and very clearly one of these resistors is K minus 1 times R. This amplifier, okay, can create gains, okay, greater than 1. Is that clear? Okay. Now let us say this error voltage is VE. In steady state, what is the value of VE? 0, right? As long as you have, if you have an ideal integrator here with any omega u, okay, you apply a DC voltage VI, the output will go to K times VI, irrespective of what omega u is. As long as it looks like some kind of integrator, that will happen. You will, in later courses, you will see why. If you want to apply a sinusoid here, then the value of omega u matters. In this course, we will assume that omega u is very large anyways. Even if you apply a sinusoid, okay, you can assume that the gain of the op amp is very large.
So we told that VO is A times VE, no, sir?
Yes, correct.
But A is infinity and V is 0. So
VE is 0 because A is infinity.
So to make the value of K, right?
Correct. That is right. Okay. VE is 0 in steady state only because A0 is infinity. Okay. Is that clear? Now, the fact that VE goes to 0, okay, this has a very specific terminology. The op amp is said to create a virtual short between its two terminals. Okay, the op amp creates a virtual short between its two terminals under very specific conditions. Okay, only when the op amp is placed in negative feedback. Okay, virtual short only when placed in negative feedback. Okay, I'll emphasize that, I'll repeat it again. When the op amp is placed in negative feedback, okay, and its gain is assumed to be very large, the voltages, the error voltage at its input goes to 0. In other words, the voltages of the positive terminal and the negative terminal are equal. Okay, and this is called a virtual short. It is of course not a real short. A real short is when you just connect them using a wire. This is a virtual short, and it's very important to realize that this happens only when the op amp is placed in negative feedback. Okay, and that's why I'm repeating it again and again and again. Now, this is actually has very interesting properties. Okay, because we called it a virtual short, but what is the current flowing into the op amp? It happens to be 0. The current flowing into the terminals of the op amp are 0. What does that mean? It looks like an open circuit, right? If only when you open circuit two terminals, there is no current flowing between them. So you notice that when an op amp is placed in negative feedback, the op amp generates what looks like both a short circuit and an open circuit between its two terminals. Is that clear? It creates what looks like a combination of a short circuit and an open circuit. Okay, this is very important. Any questions? Yes. How do you know the current is 0? That is the characteristic of an ideal op amp. In fact, it should be a precondition, because if the current were not 0, this will not be at VO by K. Correct? If there were a current flowing here, if there were a current flowing here, the voltage at that point where you want to generate the comparison, it will no longer be VO by K. It will be something else. Okay. One of the preconditions of using an element here to compare and generate the output from the error is that its input current should also be 0. Okay. So this is often called a virtual short, and sometimes if the input of the op amp, if one of the inputs of the op amp is actually connected to ground, you may also hear people talking about a virtual ground. Okay, there are some configurations where one of the input terminals of the op amp is connected to ground, to a reference terminal. So you may also hear it being termed as a virtual ground. Okay, people use these terminologies a little bit loosely, but that is fine. Now, the fact that it needs to be placed in negative feedback is very important. Let us try to analyze first of all what will happen when how to analyze this circuit when A is not infinity but very large, right? So now, knowing all you know about the op amp, right? What are the characteristics of the op amp? It has a very large gain. Okay, its input current is 0, right? What can you replace the op amp with? The simplest model that you can replace an op amp with is a what? I want to build this amplifier of gain K and analyze the circuit, get the gain in terms of A0, right? So what do I replace the op amp with? I need to replace it with some kind of circuit element or elements. Yes? Voltage controlled voltage source, that's right. You can replace it with a voltage controlled voltage source of gain A0. Okay? So between these two terminals, so I have V plus, V minus, and I can A0 times V plus minus V minus. So the op amp itself can be replaced by a voltage controlled voltage source whose gain is very large, whose gain is A0. Okay, there is no input current into the op amp. The output voltage is related to the difference between the input voltages. These are the properties of the op amp. Now we will place the op amp in negative feedback to get a gain of K and see what happens. I am just giving it with respect to some reference ground, okay, which may be internal to the op amp. So this terminal is connected to VI, V plus. The negative terminal is okay, this is VO, this is VE. Is that clear? So this voltage is VO by K. Okay. Now tell me, can you find out for me VO by VI? What is the expression for VO by VI? In steady state? A0 times VE. VO is A0 times VE. This is A0 times, correct? So from this I can find out VO by VI. What is VO by VI? Give it to me in terms of A0 also. Don't set A0 to infinity. A0 by A0 by 1 plus A0 by K. Okay, this is one expression. You can write it in many different ways. You can write it as K by 1 plus K by A0. You can write it in that form also. Okay. In fact, that may be the useful form, because I want to write it as in this form, because it is easy to see what happens when A0 goes to infinity. When A0 goes to infinity, this will just go to K, which is what you want. Is that clear? So this term will just go to 1 when A0 goes to infinity. What is VE in terms of I will write it here. What is VE? What is VE in terms of VI and A0 and K and so on? Into Is this right? K by K plus A0. This is the expression for VE. Is VI into K by K plus A0. When A0 tends to infinity, VE should go to 0, and it does. Right? So it's very clear, right? And if you had initially just set these two voltages to be equal, you assume that A0 is infinity, it is very clear that VI has to be equal to V0 by K. This is a very simple circuit. Okay, but if you have a more complex circuit, you may want to find it out in terms of A0 and then set A0 to infinity. Now what will happen if I look at the other circuit which does not have negative feedback? How do I generate a similar circuit which does not have negative feedback? Very easy. I'll just flip the signs of the op amp. I'll just flip the signs of the op amp. What will happen? What do you think will happen first? What will happen if you flip the signs of the op amp? First of all, is this still negative feedback? It is not. It should not be, because VE, okay, will be generated such that it will move VO away from the desired value of K times VI. Okay, VE will be generated such that it moves VO away. You can put in initial values for VI, VO and K, okay, and figure out what will happen. But if you try to put in the equivalent circuit as a voltage controlled voltage source for the op amp, what do you think you'll get? Go back here. If you just change the sign of VI, what will happen? VE will now become minus K by K plus K0, K plus A0 by VI. No, actually there will be a negative sign here also. Okay, but basically what you'll find, you can work it out, I'll give it as a homework. You figure out, you draw the equivalent circuit for the op amp as a voltage controlled voltage source and figure out what will happen. You will find that if you set A0 to be infinity, you will still get the same values as before. Okay, even you will still get the same values as before. but the equivalent circuit of the op amp as a voltage controlled voltage source is not applicable when placed in positive feedback. Okay, you can use it only when the op amp is placed in negative feedback. Okay. Do not use the VCVS model in the case of positive feedback. Any questions? Any questions on the op amp? Okay, yes. What factors do A0 depend on? A0 depends on what is there inside the op amp. It is too early for us to understand what goes on inside the op amp. Does A0 depend on omega U? There will be some interdependence, yes. Anything else? Okay, so in tomorrow's or in the next class, we will try to find out, on Friday's class, we will try to figure out how to analyze or how to figure out whether the op amp is placed in negative or positive feedback. Right? You need to be able to identify whether the op amp is placed in positive or negative feedback. We'll do that on Friday's class.